Good morning, everyone. Thanks a lot for coming because it's early and the hall is full. So on this first transparency, you see my life trajectory. But don't worry, I'm not going to show you my kindergarten photographs. The Nobel Committee asked me to tell you the story behind it, and it's a rare occasion to tell a story which led to this prize. So my timeline starts in 1987 and finishes with the submission of our paper. After that, Kostya will take over and describe properties of graphene. Let me start, probably appropriate point, with my PhD. So all I would like to tell about this PhD is the title of it: Investigation of Mechanisms of Transport Relaxation in Metal by Helicon Resonance Matters. Does it sound exciting? Let me assure you that it was as exciting as it sounds now. But every cloud has its silver lining, and I took the most of this experience and try to avoid dead projects, boring projects, never again. And I hope for the next 20 years I tried exactly this. So after the PhD, I became a staff scientist in Russia, and the first thing to do was to find something new, but still possible with the facilities. I was looking for new experimental system, and new and possible with facilities in late 80s was something like of an oxymoron at that time. So still looking around for a couple of years, I found a system in which, a superconductor projects strongly inhomogeneous magnetic field on a studied system, and there were quite a few papers which went late in mid-90s later, and how electrons behave in this strongly inhomogeneous magnetic field. The experience I took away that it's much nicer to find a new experimental system than try to find a new phenomenon in a well-studied system. Since then, it was the search for new experimental systems. In 1990, at the age of 32, with H-index approximately 1, which was mostly due to self-citations, with poor English, I entered the Western job market for postdocs. So I spent 4 or 5 years as a postdoc at different places. During this time, I studied mostly semiconductor physics and those subjects I studied. Only one story I like to tell from those 5 years is during my first 6 months visit to the University of Nottingham, it's very hard to find for a postdoc or a visitor something that can be done within 6 months. So my hosts at that time, Lawrence Eves and Peter May, looked what they had, and somewhere in their drawers there was a sample which was studied, done and dusted, published before they gave me this sample, and during 6 months I managed to produce enough results to publish a couple of decent papers afterwards. So the experience I took away, which I use to tease my younger colleagues these days, is that there is no such thing as bad samples. There are only bad postdocs. So if you look carefully enough, you'll find always something. It was time to move on, and I became an associate professor in Nijmegen. And again, the first task, which I already knew how to do, is to find your research niche. Something possible, but something different. So what I was mostly studying is what I call later mesoscopic superconductivity, and facilities were, of course, not Russian, not Soviet facilities, but I still use structures from different places, from Nottingham. Lithography to make those structures was done by Sergei Dumanos, and measurements and analysis and writing up were done in Nijmegen. In red, you gradually see the names, how they appeared in history of my life. Those names contributed to this paper, which was awarded. So after being established, there was some free time after 3 years, and at that moment I started something what nowadays called Friday night experiments. So the first Friday night experiment came because of the following, okay. At this lab there were ancient magnets, 20 Tesla, strong magnets, but they required a lot of power, gigawatts of power actually, and required extra cryostats to do any experiments. So, and my boss at that time pushed me, okay, try to find something we still can do. And I was asking myself, what is competitive edge? And competitive edge, I did find that many people have similar magnets, but okay, a room temperature bore was not available for everyone. So the idea was to see something room temperature phenomena in those strong magnetic fields. And phenomena I found in literature is magnetic water, so-called. I can't tell you, I don't have opinion about this controversial subject still, but essentially you can buy small magnets, put them on the tap of your kitchen, in your kitchen, and allegedly the scale chalk in hot water pipe on your kettle disappears. Sometimes it works, some doesn't, no one knows why. So the idea was, okay, if we have so strong magnetic fields at room temperature, why wouldn't we just try to see what happens with water, not in the field of a permanent magnet, but much stronger field. So what I did, I just poured water inside this magnet. Don't know why I did it. Okay, it was not very scientifically to pour the water inside a magnet, but apparently there are these sort of facilities all over the world. Okay, several labs have those, and yeah, and they existed for a few decades, but no one did it before. So I expected water to end up on the floor, but instead of that, I saw that the water floating around, levitating inside. It's a very therapeutic movie. I like watch it for minutes and minutes, and but let me skip this because the phenomena behind it took an hour to calculate all the numbers, put them correctly, and the phenomena behind is diamagnetism. Everyone knows what diamagnetism. Okay, if those who do not know, it's a very weak magnetism. You, water, everything around possesses. We were actually scooped, okay, 5 years before there was a paper in Nature reporting room temperature, non-magnetic materials levitating in strong inhomogeneous magnetic field. When I didn't notice this paper, no one of our colleagues did notice the paper, and so, but we were working with strong magnetic fields, so, but looking through literature, we did find this paper, and something missing here. Usually when you present some scientific results, you have a plot or a picture, and there was nothing. So I thought that it requires emphasis, so to convey a message that so-called non-magnetic materials are still magnetic, and my colleagues came with all sorts of brilliant ideas what to levitate, from cheese to pizza to tomatoes and strawberries, but eventually, okay, we'll find something which caused a wow factor. It was a frog. If frogs can fly, pigs can fly, and humans can fly too. So you think that Nobel Prize gives you a lot of publicity. This frog redefined word a lot. So, okay, that was a lot of publicity. Behind this superficial noise, actually, there was a very important message. Perception of high magnetic field and diamagnetism did change. It's no longer perceived as feeble phenomena. In many textbooks, you can find this picture, and it's a common for me that at a conference something comes across and tells me, oh, I know you. I don't understand anything about graphene, but your frog. I start my lectures usually on physics or on condensed matter physics or magnetism. We're showing this picture and it attracts attention of students. They like to learn why the frogs can fly, what is the phenomena behind. So from this I took an experience that even obsolete Asian facilities can offer a competitive edge, and the sign line experience was that don't take yourself too seriously after I received the Ig Nobel Prize in 2000. Time to move on. Together with my wife, later joined by Kostya Novoselov, I moved to Manchester, and it was essentially an empty lab, a little startup, and no central fabrication facilities, which are absolutely essential for doing experiments. So the first task was to establish yourself in a new country, in a new lab, and set up new facilities. So we did, with the help of, again, Sergei Dubanov's lithography in Russia, I continued the same line of research, and we started publishing papers of high quality journals. And by 2003, despite these first facts, we get a well-equipped lab and state-of-the-art microfabrication facilities. When you settle down, it's Friday night experiments like bicycle experience. You learn once, you can never forget about this. So one of the first of those was the mechanism behind geckos climbing ceilings and walls. How do they do this? I learned about this from reading papers by Autumn, and its mechanism is extremely simple. Toes of geckos are covered with tiny hairs. Each hair sticks to the surface due to van der Waals force. It's minute force, but billions and billions of hairs put together create a formidable force enough to keep geckos. What shocked me in this experiment mechanism is so simple, and the spatial scale in this experiment was exactly what I used to work in the lab. So the idea was to mimic the same mechanism, but creating an artificial sort of tape called gecko tape these days. It never worked as good as real thing, but at least it was a proof of concept. And learning how to do wow effects, there was only 1 square centimeter of the tape, so we can't put any student outside the window, so we finished up with a demonstration that it's still sticky and on the same principle. Usually when you talk about Friday night experiments, people say, oh great, next Friday I'm going to do that, okay? In fact, okay, there were very many failures. I tried to list those, but there was no enough space on my transparencies, but what I have found, it's very strange. When I list those, I managed to remember around 24 of those failures. Some of them were near misses, actually, and I'm still trying to move over the experience. You expect that failures would be more often, okay? Successes would be much rarer than they occur. It probably means when you move from your area to something new, you have a very high chance succeed in finding something new out there rather than within your research area. Now, again, this backdrop, we come to graphene, which originally was also this type of a Friday night experiment. And the idea behind, I tried to analyze how did it come, and it did come from 3 little clouds. One of those thought clouds was metallic electronics. Essentially, the idea is a century long. You put a piece of metal, apply electric field, you change number of electrons, change conductivity, and so on. looks good, do the same as transistors do, but with a metal rather than semiconductor. But then you put numbers together and find out that induced concentration is only a small percentage of what is in a single layer of a metal within. So, and you can rarely go to thin enough film. So people did try it for a century. The first actually was Charles Mott, father of Sir Neville Mott, who was a Nobel Prize winner in physics 35 probably years ago. And J.J. Thomson gave him exactly this task to change concentration of electrons in copper or in something like that. It was all the list of failures. I probably learned this mostly from Viktor Petrashov. Yeah, that was, I didn't look into this subject, but it was at the back of my mind all the time. So what I was tinkering is to do something different. We all know that it's possible to grow epitaxial films, and the new element I was thinking, if I remove chemically the substrate, there will be ultra-thin monocrystal left. Well, it might be thinner than usual that you can do by evaporation, but also, what is important, quality of this would be good. So I was scouting for different epitaxial systems, but never was offered more than a few nanometers thick aluminium from Nottingham University. I didn't study it. I thought that it's too thick and it won't work anyway. So, but it was on the back of my mind. The second clouds came in 90s, where there were so many nice, great papers about nanotubes and especially nanotube transistors. I was at many conferences, reading many journals, and each time I was salivating how to do something similar but something different to what people were doing. It was a point on envy when people managed to make so nice results at that time. The third one was equally important. It was literature, especially from Millie Dresselhaus' review, from which I learned that it's people, despite hundreds of years of studying graphite, they know not everything about graphite, and there was nothing about thin films of graphite, which rather hard to do, and approximately at the same time there were several provocative, let's name it so, papers from Ashkenazi Kopelevich groups, which also tell me the same story. Thin films of graphite can be interesting systems. So all these three clouds merged together into something like a PhD project. And PhD project was to make graphite films as thin as possible and study whatever, metallic electronics, whatever God will send us. So essentially, a new PhD student, Dajan, was given a tablet of graphite, and I asked him to use our fancy polishing machine we acquired at that time to make as thin as possible graphite. And after a few months of work, he came to me with a petri dish and with tiny flake of graphite at the bottom, all what left from this tablet, and he says, I have done it. And I looked in the microscope. It was 5-10 microns thick, so no point of studying. I said, we're not going to do that, okay, because it's too thick. And yeah, but the tablet has gone. At the same time, Oleg Shklarevsky was a senior postdoc in the lab, and he said, why are you doing this? And it was my mistake, actually, because of highly oriented pyrolytic graphite. Somehow I gave high density pyrolytic graphite, and it doesn't cleave as nicely as the latter, the former. So Oleg allegedly saw this unsuccessful experiment and ran away for 5 minutes and brought a sellotape with graphite flakes left on the sellotape, and people say that he digged it out from a litter bin. That's a legend anyway. So it was obvious in a microscope that flakes here are much thinner than the flake which left after polishing. So polishing, my idea was that Scotch tape started to be ruling the world at that time. So if you look through the tape, you find out that the pieces of graphite are really thin, some of them transparent to light when you look from the backwards. This piece is here probably, or this one, probably only 10 layers thick, as we know with the benefit of hindsight. So it took a few months to go to down layer. It's still a small piece of flake, and a couple of years later we got a big graphene crystallite, single layer crystallite, visible by naked eye. And for me it was shock. I came from semiconductor community. I knew film deposition, semiconductor physics, a little bit molecular beam epitaxy, and I have read before and during a lot of books, a lot of reviews, how difficult it is to grow monolayers. They always try, even in high vacuums, they coagulate, in air they oxidize, and growths are usually so-called island growths. Then I was reasonably well educated. I knew also another argument comes from Mermin-Wagner's theorem, that in order to grow anything, you need a temperature close to the melting temperature, and at this temperature, vibrations diverges in 2 dimensions, not in 3 dimensions, and everything goes 3D. So essentially, 2-dimensional growth, unless you do it at very low temperature, is completely forbidden. And sometimes people misuse this theorem applying to graphene at room temperature. You have to apply it at the growth temperature. Then you look also, I looked in the literature further, and specifically for carbon, it was known that flat sheet is actually thermodynamically unstable until you reach sizes of the order of 20 nanometers sheets in diameter. It's a lot of atoms together. Before that, all 3-dimensional shapes are more favorable. So the question how to get to that large sizes without passing through inner growth through these smaller sizes. Even if you grow a large size crystal, the simple thermodynamic arguments tell you that graphene sheet is not stable, it should scroll on. All those arguments remain valid today as well, and the only reason graphene exists because the same reason as diamond exists. It's less thermodynamically stable than graphite under ambient conditions. So we're dealing with a system which is metastable, but it's still possible. How to obtain graphene? It can be obtained only through 3D growth. I do not know how to obtain it differently. So either you grow graphene as a plane of graphite and then split it, as we did, or you grow graphene, as I described before, epitaxially, and then somehow remove or detach the substrate from this one. That's the only way. This is probably why it took so long for graphene to be isolated. I came from community which never dealt with carbon. It was obviously something different experience for people dealing with graphite and carbon nanotubes. Of course, okay, to publish a paper, you look carefully through literature. People saw nanoscrolls grow reasonably thin, 60 graphene layers thick graphite film. Studied that. People grow graphene on top of metals, on top of graphite, and so on. We added to this literature a little bit later, and I'm pretty well aware of all the history which was behind. So I think the closest observation of graphene of isolated graphene was in paper by Hiroshi, and they observed in TM faults of graphene which corresponds to a single layer. Also Ebbesen in 95 they make something like origami, still several layers thick and on top of graphite, but it was a very close attempt to do. Several people grow single layers of graphene, but they were still coupled with the substrate and not isolated. So whom should we attribute the discovery of graphene? Digging through the old literature, I did and other people did. I think it's fair to say, if not Romans or medieval people in Britain who discovered deposits of graphite near in the Lake District, it's probably Benjamin Brodie in 1859 who put graphite into several acids, and as a result, looking through his paper, he probably saw something like that, a deposit of soot of graphite, and then in water some yellowish liquid, water solution. He called it carbonic acid, and actually thought that he discovered a new element, graphene with a molecular weight 33, he believed. It turned out not true, because now we know that it's suspension of graphene crystallized. This is what he was looking at. This is what gives the color. And 100 years later, people put dry residue of whatever floating here in transmission electron microscope and looked and found out flakes of graphite floating through. Some of them were pretty thin, and I'm not sure that those were monolayers, because the argument was about, okay, contrast given, and we know that it's very hard to distinguish between single and bilayer, impossible single and bilayer by contrast or trilayer. So, but the intention was there, flakes of graphene were also there, so for the sake of argument, it's probably the best observation for 40 years until Hiroshi found those faults. Of course, what we did in 2004, we demonstrated unambiguously that those single layers could exist, and we suggested a way for everyone to get those monolayers. If it would be it, if we just put in FM or optics or TM the same images, I think it wouldn't expire any further work. It would go probably into oblivion like this work for I don't know how many years. We did actually something else. We take from this tape a small crystallites of graphite and make devices of those. That's a flake of graphite of the size of a hair, 50 microns in this direction, 100 microns in this direction, and there are, with toothpick, you put a silver pane context to this device. And this done by Kostya, and it really requires experimental skills. I know only Kostya, myself, and maybe one or two more people with whom I ever worked could do similar small things on there. So what was surprising, and this is 2003, August 2003, that those devices worked. Actually, they worked, they conducted, all contacts were working, and most importantly, if you apply voltage to the substrate, the resistance of the device changed. Remember this metallic electronics, we got not 1 by 3%, so it worked like metallic transistor. Only a mad person can call 1-3% metallic transistor. But I looked at this, and it was, for me, it was an eureka moment, because such ugly looking devices with such ugly looking contacts and so thick already showed something. And I thought, oh, what would happen if we apply all the range of technique we have available in the lab, including lithography? That took quite some time, and within a year, we went down to layer, make devices, down a little bit later down to a single layer. They showed not few percent, but 30% ratio, and we published it in Nature. It was a hard job not only to do that, but also to publish. It was twice rejected by Nature, And there is a message inside. If someone of you recently been rejected by one of those glossy journals, never give up. It could be a Nobel Prize winning paper. So why this paper important? If we, of course, observation and unambiguous isolation of graphene crystals, it's cute, but that's not what was paper about. If those two, it would go to oblivion. What we did, we found out that with the gate, with change in voltage on the substrate, we can change properties of this material. Take a film of gold. Whatever you do, it will be a film of gold. Here, with external electric field, we change graphene from a metal which has a lot of electrons to a good metal which has a lot of hole carriers in this regime, through a regime where it behaves like a semiconductor. It's a lot of properties within the same device. We called it ambipolar electric field effect. And changes are huge, not 1%, 100 times already in this paper. Most important, probably, the quality of the paper. It's what this is. People normally know that the thinner the film, the worse the properties of the film. Here you get a monolayer, which is not in high vacuum, not at low temperatures, under ambient conditions, with a lot of absorbate, with a lot of lithography residues on a rough substrate. And despite that, electrons travel through this shit like bullets without experience all the weather outside. Even with the benefit of hindsight, you can't predict that it would happen for a monolayer. Let me put it this way. If the quality of graphene would be 100 times less than we reported in our first paper, I wouldn't be standing here. The quality is very important, and many phenomena we found is due to quality. So what this paper did, it reported not just an observation of graphene, but rediscovered it in its new incarnation of a high-quality two-dimensional system and beyond. During the next few years, we start studying this, found massive massless Dirac particles, 2 new times quantum Hall effect, universal optical conductivity, Klein tunneling, tunable, and so on. Kostya will discuss some of those properties in his talk. Many other groups contributed to those beautiful observations, contributed to this work, and also reported their own beautiful observation of various many phenomena. So it's like philosopher's stone, okay? What turned out, whenever you touch any phenomena with graphene, addressing in graphene, it turns out something new, something unique. It's really a very rich system which we didn't experience before, in fact. So my time is up, and my timeline finishes exactly at mid-2004, and I leave the pleasure to acknowledge all our many collaborators in the last 6 years to Kostya, and let me acknowledge only the people who contribute in this initial work. Serge Morozov did measurements, as well as Kostya, of course, and crystallites were provided by DA. 3 people involved in microfabrication. It was a big part of job, and Irina helped with writing up and some observation. And with this, I'd like to thank you all for your attention. Thank you. Thank you.